hexagon format with dashes and wedges. We're not using chairs, just dashes and wedges. Try and anticipate what you think this means. Again, this is what I would do if we were in lecture together. I would draw this on the board, walk around and look what you've done. You really should fill this in on yourself. It's okay if you get it wrong. It's not okay if you don't try something. Even if you're confused what I'm saying, try something. What do you think the product looks like from this one step? And what I'm hopeful is that many of you were able to draw the two methyl groups trans to one another, or the methyl group here and bromide cis to one another. This particular carbon here is this one. We have a methyl group up, hydrogen down, and on the same side we have a p orbital. I'm saying let's think about what happens if we push bromide in from the top, into the top of this p orbital. This methyl group gets pushed down, and this is what the product would look like. And 50% of the time, this happens. And what happens if we did from bottom? What if we pushed bromide in from the bottom? I'm not going to draw it on the same picture. That doesn't make a whole lot of sense, right? This mechanism really shouldn't have things going into two orbitals at the same time. But if bromide comes from the top, it leads to this. What do you think? If you got this one wrong or if you got it right, draw the product that you think would result, on the other hand, if bromide came in from the bottom p orbital. As it's coming in from the bottom, its electrons are going to form a new bond, and these ones are going to start being repelled upward. So please draw that product there. I'll give you a little bit of time. Giving you enough clues now, you should definitely be able to do this without too much prodding. In fact, I gave you the first answer. I was hopeful that some of you could have got this. If you didn't get this, I'm hopeful now you'll redeem yourself and get the other one. Just going to draw hexagon. The methyl group and hydrogen don't change. But the stereochemical outcome here has changed. Imagine if bromine comes from the underside of the molecule and pushes the methyl group up. This one stays the same in both. Nothing's happening here. We're not doing anything here. And it's okay if you have your hexagons rotated a little bit or rotated sideways. The key point is all the unique substituents will be 1 and 4 carbons away. So if you have this rotated 90 degrees, 60 degrees, anything is okay. But we can just call this the 1 position, this the 4 position. The top molecule, the methyl groups are trans, and the bottom molecule, the methyl groups are cis to one another. And these will be formed roughly 50-50% yield. I'll ask you to do problems like this on cyclohexene type molecules that already have a chiral center built into them. When you see this, it's a clue that I'm asking you for the stereochemical consequences of this reaction, and I would write that in English. Don't worry, not all the problems are this complicated. Just go back in time 10 minutes. Some of the problems are this simple. It's just simple molecule, flat alkene, no chiral centers. We don't have to think about adding top and bottom. It has no consequence whatsoever. This is the simple, this is the foundation. This is the one you practice first. Then, you take this example. You redraw it a couple times. You practice these arrows. You think about the steps of selecting the better carbocation and rejecting the less stable one. You practice drawing the more stable carbocation. You recognize that there's a top half of the molecule that has an empty p orbital and a bottom half. You don't necessarily have to draw this sideways picture. You could just do it here. You can look at this carbocation and say to yourself, there's an empty p orbital. Half the volume is up above it, coming out towards you, and a bromide could come in from the top here, and the methyl group would get pushed down. The other half of the time, the pen could come in from the other side of the molecule, from the bottom. And if bromide came in from the bottom, this methyl group will get pushed up, and bromide will be on the bottom. And this happens 50-50% of the time, because the p orbital has 50% of its volume above and 50% of its volume below. It doesn't matter which lobe we put the electrons into. Carbon will be happy either way, but the net result is that we'll have different stereochemistry, whether it comes from top or bottom. So these first 3-4 slides, 3-4 examples we did here, the most important for you to develop your fundamental understanding of this. Let's do 2 more examples, and then I think it'll be break time. Yay for us. Our second case, our first case was strong acid. Our second case will be alkene plus concentrated sulfuric acid. This is going to be similar. This should be concentrated, C-O-N-C. Use concentrated sulfuric acid. Be very, very similar to HCl, HBr, HI. Has some differences. So let's just take a simple one. We'll go back to the basics. Take propene. I'm going to draw the correct Lewis structure for sulfuric acid. It's okay, sulfur is violating the octet rule. It's in the 3rd row of the periodic table. It can adopt many more electrons than 8. And we know that sulfuric acid is a strong acid. I think we did actually use it in our acid-base work. And we know that this reaction will proceed the same exact way as before. Like if this was Cl or I or Br minus, it's just a little bit more elaborate and exotic, but nothing to be too panicked about. We know that there's 2 possibilities where we can form this carbon-hydrogen bond. Rather than flip back through your notes, just try and think. Should we form a new carbon-hydrogen bond at position 1? That means there'll be a carbocation at position 2. These are just arbitrary to keep track of things. When I'm doing this, I don't want to make mistakes. So if I make a carbon-hydrogen bond at 1, carbocation is at position 2, what type of carbocation would we have if we formed it at this carb? Primary, secondary, tertiary? We'd have a primary carbocation. Okay, that's not very good. What if we took and formed a carbon-hydrogen bond at position 2? Then our carbocation would be at position 1. What type of carbocation would that be? Primary, secondary, tertiary? It would be secondary in this case, right? So we're going to reject the possibility of forming carbon-hydrogen bond here. We're going to form the carbon-hydrogen bond in position 2. Maybe in our notes we could write at 1 leads to primary carbocation. So we're going to reject that. But at position 2, it's going to lead to a secondary carbocation. Maybe we should keep that one. Let's just draw that secondary carbocation right now. So I just made a little shorthand note. Not going to draw these right now, but you guys should when you are practicing these examples. You should put it upon yourself to draw both possibilities out. Again, for brevity's sake, I'm not going to, but I expect that you should. This will be our secondary carbocation. And with this secondary carbocation, finally we'll have sulfate floating around. If we draw this conjugate base, sulfate, well, it just adds exactly the same way that chloride or bromide or iodide would add. And so it's a little bit of a pain to draw this whole thing, but you're young and vigorous people. You can do a little drawing on this Monday morning. I'll kill you. And this is the product we get. And it's exactly the same as if we were adding HCl or HBr or HI. So it's very, very similar in a sense. There's only one difference about this reaction, and this particular thing I want us to memorize. We're not going to worry about the mechanism. If you take this particular functional group, which is called the alkyl hydrogen sulfate, and that's not important. This functional group is called the alkyl hydrogen sulfate. If you take this particular compound, mix it with water, and heat it to reflux, which means boil, this molecule falls apart and makes an alcohol where the alkyl hydrogen sulfate group was. Okay? Just want us to memorize this step, and it gives this. Okay? How it works, not important for us. Trust me. But this particular function group is unstable. We have some water, we heat it, we can convert it to an alcohol. This is the thing that's different about HCl, HBr, and HI. If we had Cl here, Br here, HI here, we heat it with water, nothing happens. Carbon-bromine bonds, carbon-chlorine bonds, carbon-iodine bonds, pretty stable. If we take this alkyl hydrogen sulfate group, this group here, it's a little delicate, a little bit of water, heat, off we go. Or off it goes. Let's look at our third reaction. Our third reaction is going to be very, very similar to our second and first reaction. Our third reaction, we're going to take alkene plus dilute sulfuric acid in water. So we're going to take our alkene, we're going to add a little bit of sulfuric acid in water. The way this reaction would be written, we saw a couple variations in the notes, the pre-lecture video. The way that we'll write this is, we'll write an alkene, and in the previous example, the only two things I showed were these two things. These two things, nothing else. There's no water written anywhere. Till the very end, this is very different. This is the second step. But when we see these two things, we're going to do this reaction. Very similar to HCl, HBr, HI. But we might write H2SO4 here. We could write the word dilute, or if water is written underneath this arrow, this location here, underneath a reaction arrow, is typically reserved for the solvent. This one location underneath the reaction arrow is typically reserved for a solvent. And a solvent, you'll recall from general chemistry, is something used to dissolve something, and usually you use lots of it. Another way to think of it is that there is a great excess, huge amount, and that leads to the conclusion that this is dilute. Okay, so probably for our exam Thursday, I'll just write dilute and have water underneath here. That would be different than if there was just this written here. No water present, but now there's water present. And we saw in our pre-lecture video something slightly different happens to what we've been doing previously. Water and alkenes don't react, but we already know that alkenes and strong acids react. Okay? Let's follow through. We're going to have mostly similar things here, but there'll be a few small differences. When those differences emerge, I'll point them out. We have an alkene that's unsymmetric. We've done this type of problem 3-4 times now. Hydrogen is going to form a new bond at one of these two positions. I'm not going to go through and spell it out anymore. So slowly. We've actually already seen this molecule with HI just a few slides back. So we know that tertiary carbocation is going to form. Hydrogen goes to position 2, tertiary carbocation. If hydrogen went to position 1, we'd have a primary carbocation. That's not even competitive for this, so the tertiary is the only choice we make. Now, previously, we had sulfate adding in the last example. But this is very dilute in this case, and water is in huge excess. You can just draw water everywhere, or you can just write that it's in excess, or that there's lots. Maybe there's 10,000 water molecules for every sulfate molecule. Just think that when you do a reaction, it's only done at like 0.1 molar. There's about 1-2% of this in, 99% of this, maybe 1% of this. So this is the situation we're at now when we have water present. This is indicated when we have dilute sulfuric acid in water. It means there's not a lot, there's a lot. This carbocation wants electrons. This carbocation doesn't care where it gets electrons from. It gets it from the first pair of electrons that comes by. It's a very promiscuous and reactive species. It does not care where it gets electrons, it just wants them. So we have tens of thousands of more molecules of water than we do of sulfate. Water attacks any one of them, and it just goes right into the empty p orbital, and we're going to draw the resulting product. So the situation changes as soon as we make this dilute and do the reaction in water. Water has electrons. This wants electrons. We're going to make a new covalent bond between oxygen and carbon. Nothing else changes. Oxygen still bonded to hydrogens, still has one pair of electrons we did nothing with. Right? This is the pair of electrons that we made a new bond with. Carbocation desperately wants electrons, violating the octet rule. It's violating the valence rule, has a plus charge on it. Electrons, sure, oxygen can share these to make a bond. There's a formal charge somewhere in this molecule. You should have spotted it fairly quickly, that right here on oxygen, we have a plus formal charge when this happens. This is called an oxonium ion. It's very acidic. And what we do in this reaction to finish it is, we're going to take our sulfate base, it's a very, very weak base. We're going to do an acid-base reaction here. This is very, very acidic. We're going to do an acid-base reaction to finish this. Our final product, as we saw in the pre-lecture video, is an alcohol. This is how it works. And the byproduct we make here is sulfuric acid, which we could say is regenerated. And this particular sulfuric acid molecule, if we only have a little bit of it, every time we do this reaction, it gets regenerated. It can go back and start this reaction over and over again. Another way that we could say this particular acid here is used as a catalyst or a catalytic. Tiny amount of this acid is necessary to do this reaction. It starts by making a tertiary carbocation. This tertiary carbocation now has no choice in the matter. It has tons and tons of water around it and not much of this. Picks water. Water adds. We get this new species we have to look at very carefully. But our ultimate goal that we saw with acid dissolved in water is to make alcohols. So this connection we should be making. Alkene, strong acid that's diluted in water, will make an alcohol at the end. So this particular product is also very unstable, or intermediate I should say. It's unstable. This is an oxonium ion. This looks very, very similar to hydronium ion. This functional group here looks very similar to hydronium ion, and we know it's very acidic. And in this reaction, our end goal is to make an alcohol. These are the major products isolated from this reaction. And this particular mechanism helps us explain that. So this is a lot of stuff to digest. Let's take, let's take a 9-minute break or so. Come back at 10:20.